Okay. Good morning, everybody. Or shall I say good afternoon? Thank you again for joining us for this session, Shop Floor 5-Axis Programming with Cycle800. I'm your presenter, Chris Pollack. I'm a dealer support specialist with Siemens. My contact information is on the slide in front of you. After the presentation has been gone through, if anything comes up or you guys ever need any additional help or support, feel free to reach out to me either on my phone or probably preferable would be on the email address in front of you. Coming up after this session, we're going to have our next two online seminars. It's going to be covering the 808D control from a turning variant. So we're going to do some setup and programming on an 808 lathe system. And then after that, in September, we're going to be doing our first service training. This will be kind of more of a preventative maintenance kind of scenario, so it'll certainly apply to technicians as well as end users, specifically when it comes to recovering data, backing up data, and that kind of stuff. So look forward to seeing these next two seminars coming up. Today's content will specifically be looking at the 828 and 840 platforms or control systems. There may be some slight differences, but for the most part, anything you see today, assuming the machine is capable of it, the functions and features could be applied on either control platform. As far as a basic course overview about what you're going to be seeing today and working on, we're going to do shop floor 5-axis programming. So that's going to be using the Cycle800 or the Swivel Cycle. We're going to take a look at key functions from the setup side to allow you to simplify the setup of a 5-axis machine. We'll do this through cycles like a line edge and a line plane. So we're going to set up a part program in JOG, or at least the key features that are unique to 5-axis, the 5-axis world. We're going to go and create a part program in Shop Mill. That would be our conversational style interface. Once we've created the part program in Shop Mill, we're going to evaluate it in our simulation mode, and then we're going to take a look at it in an auto mode as well. From there, we are going to then transition to seeing what the same job would look like having been programmed in our G-code side. We're not going to program that from scratch. However, we have a pre-created part program. Just to kind of get you started and familiar with the mechanism, we'll do a later seminar specifically on the program guide G-code side utilizing Cycle800. And then we'll get a chance to run it in auto as well, seeing the difference in appearance between conversational and G-code. And then we can play around with manipulation and a few different things. In front of you is the example of the part, the basic part we're going to be machining today. This part is just a basic 3+2 kind of positioning job, very typical in the industry today, especially in the job shop or the shop floor environment where you're doing small piece runs, small production runs. So here you're going to get an opportunity to machine a couple 45-degree corners off a block. We're going to machine the top face of the block at a 9-degree angle. We're going to come back and put a 45-degree chamfer on one end of that surface, and then put a couple features like our pocket and our bolt hole pattern relative to some known feature. Once we get through, you should have a pretty good understanding of how to start to manipulate the fundamentals of Cycle800. So the first area we are going to look at is dealing with moving a machine around, jogging it, the offset tables, and what are some of the key functions we've set up for 5-axis machining. First thing we'll look at is just how do I move a machine around? Where's the information on the display? Well, as I start to rotate, what's it rotating relative to? How do my offsets start to come into play? What are different methods for moving the machine around in a manual or a job type of mode? From there, we're going to start to explore some key features that have been developed specifically for managing 5-axis machine tools. For our instance, we're going to look at the Swivel Cycle. Swivel Cycle is a way for us to start manipulating where the rotaries are in space, but based on data that's more closely to what our part program will be actually doing. And you can see in the upper right-hand corner kind of a picture of what a very atypical kinematic setup or machine type of configuration we would be dealing with a machine like this in 5-axis. This would be a trunnions or a table kinematic is what we like to call that. That would be a B carrying C configuration, very common in the industry. The machine we're going to work on today is configured as a trunnion style table, more closely representing the graphic you see on the display. And in that case, that's an A carrying C type of configuration. So the A rotary, which revolves around the X-axis, is physically carrying the C platter or table, which C always revolves around the Z-axis. From there, we're going to look at two specific features that will really save you a lot of time when doing 5-axis setup. Historically, that's probably been one of the big hurdles. It's just the complexity of the setup side when you get to doing 5-axis machining. Traditionally, on lower-end controls or older controls, you didn't have the capabilities of the system being able to manage where the part was in space when it came to these rotaries. So not only did you have to have the part exactly modeled in CAD/CAM as to where it was going to be in the real world, but even from alignment standpoints, you had to have it perfectly set up so it mimicked where the CAD/CAM package thought it was going to be in space. Now these machines, these high-end machines like the Siemens Control, have capabilities built into them where they can manage that. So from the CAD/CAM system, if you are posting CAD/CAM or if you're programming at the control, you only have to ever have to be worried about tool movement. You never have to be concerned with, well, what does the machine really have to do to get the part there or get the tool there? You just kind of forget the machine even exists for the most part and just concentrate on where the tool is going around the part. And some of the key features now for the machine to be able to adapt to where this part may be staged is the align plane and the align edge functions like you see here. So we're going to get a chance to explore and use them. Now, once we start to move things around in space, and certainly once we start to align some edges, the next logical question would be, where do these offsets go? How does the system actually compensate for these values? And you'll find there's certainly some key features within the Siemens realm that are not typically found in control platforms, control systems, that allow us to start to handle this stuff very easily. And certainly one of the biggest factors is what we call rotations about a linear axis. And I see that here in the lower picture where it says work offset details. If you look, you see a value of 10, and then 5, and then 30, and those are rotations about a linear axis. So the Siemens Control allows us to do these rotations, but they allow us to do these rotations where historically we'd be used to maybe doing that in the part program. We can do it at the work coordinate level. So we can have aligned the system at the work coordinate level prior to ever starting the part program. Other things we can do from advanced features, we can do scaling at the work coordinate level, and we can do mirroring. Those are the other two symbols to the right. The little 2 triangle symbol or shall I say the rectangle symbol with the factor of 1 there. That's your scaling factor. And then the 2 triangles kind of mirroring each other would be the mirroring function. So we'll explore that in a little more detail here shortly. And then we'll also take a quick look at MDI. MDI certainly can support 5-axis. More commonly, it's enabling or disabling a function real quick would be a quick way to use MDI in the 5-axis world. So here we probably do a quick little example of that. Okay, so what we're going to do is we're going to segue over to a piece of software we call CineTrain. And CineTrain is a machine tool emulator. So we should all have CineTrain up on our screen currently. And this is basically going to allow me to do virtually on a PC everything I could do on the machine tool control. So what you're seeing in gray is the machine control screen. So we're going to, that would be representing the screen that would be physically on the machine tool with all of the perimeter soft keys or software keys along the horizontal or the vertical spots. From there, we also have a basic representation of the machine's control panel. This is probably the thing that will vary the most from machine builder to machine builder. We have all sorts of different configurations of machine control panels. As well, builders can build their own, which is quite common in the industry. So when you're getting used to CineTrain and the layout of it, that's probably the one area where you just kind of got to get used to the way this one's set up, and there will be maybe some discrepancy between that and your actual machine tool you're in front of. But short of that, you'll find that everything else should be as close to being identical as you would see it on a physical machine tool. So one of the first things we mentioned is, how do I move a machine around the 5-axis world manually? More importantly, where am I looking for the information as I do move it around? So in our upper left-hand corner, we have the work field. And the work field right here, you can see here, this is your axis display, it's your feedback display. So right now it's sitting on work because the work coordinate system is being represented. If I was to hit the actual machine values, I would look at, it would say machine, and potentially it could show you this MX1 or MY1. And that's just displaying coordinates relative to the fixed machine coordinate system 0. Every machine has two basic zeros, or let's say a starting 0 first of all. And your starting 0 is the machine 0. That's where every machine is initially referenced from. So whether your machine tool has incremental encoders or absolute encoders, absolute being you don't actually have to home or grid or reference your machine in the morning, it still always has a machine 0. And that was where that machine was first commissioned from. So that's where all these numbers are coming from. That's the machine value. The work is our first real shift. I'm now staging a 0 somewhere on the table of the machine because that's where my part program is relative to. So I always want to be displaying work whenever I'm setting up a job. I see my first 3 linear axes, and now I see my A and my C, or whatever my rotary configuration is. So at this point, if I had a BC like the picture we saw earlier, I would see a B value there as opposed to a C. The industry standard is A revolves around X. So like a traditional 4th axis table, indexing table, or rotary table sitting on a machine, that would be an A axis. And then C always revolves around Z or Z axis, the Z axis. So anytime you see a C axis defined, a rotary, because A, B, and C always refer to rotary axes, or should as far as the industry standard. So whenever I see a C, I would expect that's revolving around the Z or the Z axis. And then B, if the machine's equipped with it, would revolve around the Y. And then from there, if you have this little bar graph, it means you have a couple axes or something more than we're displaying on the screen. So in this case, this machine was commissioned to also show you the spindle. And what would happen to the spindle. We're only concerned with the A and C axis, so I'm going to leave my scroll to the top. Now, as I want to move the machine around, I can start to move it manually. So manually, I'm going to crank down my override. I can pick my axis definer. So here I have a 4th and 5th axis buttons. This may look differently on the machine tool you're on, but once I select them, I can jog those axes. So if you notice, when I pick my 4th, my A starts to physically move. As well, if I pick my 5th, I start to see my C or my platter is spinning. So quite commonly, as I start to position around, I can use this or the hand wheel. Certainly the hand wheel, I would select whichever axis I wanted to spin, potentially pick an increment, one of these 1, 10, 100 for the index or the distance from each click. And then I can start to move the machine around with that hand wheel. Now, once I've moved it around, I may want to get back to a set position or a 0 location quickly. This is an area where I can now either start to use MDI, or just using our horizontal soft keys, I can use our quick reference function called positions. And position would allow me to directly command my rotaries as well as my linears. I could perform a multi-axis move here if I wanted to. So we have a tool specifically built into this simulator, a machine space emulator, we like to call it, but basically It's a configuration to show you what the machine looks like, and then as we get into auto, you'll be able to see the dynamics of how the machine moves around. So I just want to bring up the machine model real quick, just to give you a quick visual on what this machine would look like. So this would be a very traditional A carrying C configuration. This would be like a gantry style machine. So this top ram will move back and forth, the head will come up and down, and then the X will move back and forth. And then you'll see the rotary move. So as I manipulate the rotary in space, we can always return back to this machine model to get a visual on what's happening. So if I tell the machine, hey, move to an A of 45 degrees, and I'll rapid it, so we go at a higher rate of speed. I go back and look at my machine model, and now I see the A is sitting at a 45. So you notice when I revolve the A at a positive direction, the trunnion in this configuration tipped up towards me, towards the operator. If I was to go back and define a negative, which you can go in either direction, now the machine's moving over. I left it in feed, so I'll just crank up my speed. So now I'm sitting at a negative. You see the negative right here next to the A. So if I come back over to my machine space, I see that the A is now tipped up at some new position. So from there, these are positional moves, obviously based on the machine coordinate system. So this machine was commissioned with A0 being perpendicular to the Z or parallel to the spindle face. However, if you want to look at it, it's really 6 of one, half dozen of the other. So that would be my native A. So now from there, once I start to get my head around it, how do I start to manipulate where this rotary is? Well, one of the simplest, most basic things would be just to do an angular offset. So if I was to say, I want to set my A at, at a 15, we'll do a little more, at a 30-degree angle, we'll do negative 30, right? So maybe this location here is where I want an initial 0 staged. Maybe I don't, for some reason, want it clocked. What you can do is that value could have been written into my work coordinate system. If I go to my standard work coordinate system, right here as an A variable. So if I tell it minus 30 degrees right there, now you see I have an A0 stipulated. So I'm at A0, yet, if we look back at the machine's sitting at some angle. So probably the most basic ways of zeroing out a machine will be using a direct axis 0 like this, where I'm going in and I'm zeroing it. And that's pretty typical to any machine in the industry today. Usually you have some way of zeroing out your rotary axes. The problem comes in if the machine itself is not managing at this point where the 0 is in relation to center line of the rotary axes and where the platter is. So as I start to move things around on the table, even though I appear to be zeroing them out, the system's not going to compensate for, well, I swung this way, so I need to track my 0 to some new location so it can really kind of time itself. So what we've done was we've incorporated this functionality, and we see this under the offset table. If I go to details, of first being able to do rotations around linear axes, which is just another way to zero it, but we've incorporated this functionality through this swivel feature. So what swivel is really Cycle800, which is what we're going to use in the programming mode, but it's a way for me to not only move my rotaries, but the system enables a set of parameters where it's tracking and understanding where the rotary is in space and then compensating for it. So it's going to know where is my center line of A in relation to the platter of C, and where is the distance between the center of C in relation to the center line of A, if there's any discrepancy there. So if the part swings up and there is a discrepancy and everything's not perfect, which there never is, the system will automatically track and compensate for that. But that has to be done with what we call this TC, or this tool carrier, enabled, and you're enabling it really through Cycle800 through the Swivel Cycle. So if I want to, I can now start to move the machine around just like I did in manual, but I can use the Swivel Cycle to start to do that. So instead of, we're going to get rid of the 0 here. The machine is now still sitting at 30 degrees. Instead of using the position screen, I can now come in, I can enable my tool carrier. The name of this is going to vary based on whatever the builder decided to call it. This one happened to be called CC1. A lot of times you'll see the builder use their name or the type of rotary that's on the machine, maybe the manufacturer of the rotary, and all sorts of different industry standards. You just want to make sure you pick whatever the name is. The next feature that's really nice within the Swivel Cycle is the ability of managing where the spindle is. So if I wanted to return this machine back to a 0 location, but let's say for argument's sake the Z was down, so we'll take a quick look here. So the Z head is down next to the platter. So now if I had any work holding here or anything and I start to swing, I could potentially hit that spindle. Well, if I come in and tell it, hey, retract the head all the way to the top to some predefined location, then I can tell it, what do I want to do? Do I want to do a new or an additive swivel? Think of this like absolute positioning in relation to incremental. We'll play around with this a little bit later. And then how do I want to swivel? I can do axis by axis or direct, and both are going to give me the same result. You'll start to find yourself using axis by axis from the part programming scenario because it's a little easier when I have compounded rotations. I don't have to think about, well, rotary has to do what, like let's say in this machine, if I wanted to tip my system 45 degrees in the A, that's easy. But what if I needed to tip it 45 degrees in the B? Well, there is no B. So the system, you as a programmer would have to know, well, I got to spin my platter around 90 degrees to make my Y now really relative to my X, so I can then spin it around the A. So I would have to do C of 90 and then an A of 45. Well, that starts to get pretty complicated as I start to think about these things. Axis by axis, you just tell it, hey, I want to spin 45 degrees around this linear axis of Y. And the system will then say, oh, well, in that case, I got to spin my platter, and I got to spin my table, and it'll figure that out for you. But we're going to do just a simple retract to a set location. So we're going to leave everything at 0. Where do we want to go? The final thing is our direction. Whenever you do any type of 5-axis motion, there's historically always 2 potential solutions. Which way is it swinging the platter? So here, the default was set to be negative, so I'm going to leave it at negative. But we'll use this a little more, and there's some slides that talk about this in more detail in a bit. So we hit cycle start. The system returns to 0, 0. It now enabled this TC1 that was not here before. So now my kinematics are all being compensated for. When we say kinematics, that's just a very fancy term for the makeup of the machine. The rotaries, how many rotaries there are, how many linear axes there are, what's its configuration is really all kinematic really means. So don't let that 10-cent word fool you. So the system's now enabled, it's on, she's starting to manage it. What was the end result? Well, if I go back to my machine space model, I see the head is all the way up, I see the table square. So the system did 2 things. You're going to start to use the Swivel Cycle itself to really kind of manage where the system is and turn things on or off. Now, as well, I can start to set zeros. And this becomes very important because, historically, like I said earlier, the problem was where is this part in space and how do I align to it? Where does the CAM system think it is in space? So what we've done is we've incorporated 2 key functions within our Measure Workpiece tools. And those of us that have been using our control or maybe seen some of my earlier webinars would be familiar with the Measure Workpiece function as far as setting a basic 3-axis machine. And those are the same tools you'll use when it's time to actually define the 0. But the first thing we need to do, and I'm going to put a probe in my spindle. I happen to have one, so I don't need the tool change it. The probe is in here. That's great. I need to initially datum the plane, right? what plane on my rough stock or my part do I want the spindle to be perpendicular to? And what do I want my tool, we call it tool normal. So when I tell the tool to go its normal position, what is it perpendicular to? Well, a lot of times in the standard system is going to be perpendicular to the platter of the machine. But what if, in fact, the part I put up on it, the way I'm holding it, or just the type of feature, I don't want to be normal to the machine's platter. I want to be normal to some face or some compounded surface on the machine. Maybe my fixturing's not perfect, and that's okay. We let the machine align to the part instead of having to align everything to the machine. Well, we're going to use a feature called, and I'll pull it up right here, Align Plane. And what Align Plane does is that allows us to first align our initial datum surface. So the way this works is you're simply going to have the machine sitting typically at its base 0 location. So I don't want any offsets compounded. I don't want any offsets turned on. I want everything kind of zeroed off, everything zeroed out. I don't even need a part 0 at this point because it's not going to be a relative value once I apply some rotations anyway. You always want to kind of pick it in this order. You align the plane, then you align your edge, which we'll do next, and then you define your part 0 on it. And everything should now be square to itself. So the way this works is I would just move a probe down to some point on my part. So I'm going to bring her on down. We'll bring it just down in the negative a little bit. Of course, we haven't set any zeros or anything. So come down. Maybe right now I was just about ready to touch. Now with an automatic probe, all I have to do is hit cycle start. The system will feed down, touch the edge, and then save that recorded location. And I saved that value, and I see that by giving me the P1 in blue. Now you're going to do the same thing at 2 other points. So you're going to move over a little bit. Maybe Z happened to be up a little bit for clearance. Cycle started. She comes down. She touches a new point. Now I'm going to move my Y to some other location. Maybe my Z is at some other point. Cycle start. She comes down. Triggers. So it's just touched 3 points. It's about to write to whichever work coordinate I had selected here. So all I have to do is say set work coordinate, and it's now going to write in these values. Now, it writes it in, but the first thing it says is, hey, do you want to set the probe perpendicular to the plane? So if I want the machine to now move to this new location, I can do that at this point. Or I could say, no, don't worry about it. So I have 2 options here. I can say yes, then I can even tell the machine, retract before you do it. Or I can say, no, I just want to write the offsets. I don't want to move yet. So that's what we'll do. Okay. So I back out. I've just established some values. So what happened? Well, based on my align plane setup, I was writing to my work offset or not. So I was writing these values to the work offset. So how did it write these values? Well, if you look at the offset table, you see there's nothing in the rotary axis here. This is one of the base functions that starts to use the rotations about a linear axis. So if I hit details, I now see I have 2 values that were calculated based on that surface. So it probed 3 points. It said, well, this is what I would have to do to become parallel to those 3 points. I would have to do a -3-degree rotation about the X, and then tip about the Y, -24 degrees. So if I was to now tell the machine in the swivel cycle to just go to 0, 0, 0, right? A quick way to make sure if there were some numbers in here, some residual data, to zero everything out, just hit initial settings. It'll zero everything out. Make sure you give it your retract. But now when I cycle start the machine, now it's calculating these values. And I would have had no way of anticipating what these numbers it moved to. The system's calculating that. What it's doing is now, if I look at the machine, she's tipped somewhere. This is now parallel. So this is the surface on my part that's now parallel to my spindle face, or perpendicular to my tool plane. So once you've aligned the plane, the next step in the system calculating where it is, the part is you want to align an edge. Potentially a straight edge that I'm going to touch off and establish some 0 to may not be parallel to my x-axis or my y-axis. So what you do is you use the same measure workpiece. You pick the align edge. There's two features you could use. I could do the base align edge, which will just align the edge, but it won't set a 0. Or you can use the rectangular corner or any corner, and it'll, off 3 points, align the edge and also set a 0 at the corner of those. And then you can change this going around to manipulate it. I would just do a traditional line edge myself and then go back. So a lot of times I like to work from the minimum part being a 0, 0. So then I might find the center or whatnot. So line edge works very similar to a line plane. The only difference here is I can have a little more control, per se, telling it how I want it, what axis I want it to pick, what direction the probe's running in. Also, do I want to align the system based on the coordinate rotations? Those are the X, Y, and Z rotations around linear axes. Or do I want to rotate or set the axis specifically at a set rotary axis, so then I could define it. I would say, probably standard rule of thumb, I would get in the habit of aligning everything consistently. So if you're aligning the aligned plane with values around the linear axes, then I would certainly be aligning my edge based on coordinate rotation. If you're not doing the aligned plane, you're strictly just doing a base rotation, then it kind of comes into how my part program is methodized, and some configurations of how the machine tool is set up. So in a scenario like this, if I know that my program coming in is direct axis positioning, where it's calling out for C's and A's and all that, then I'm probably more inclined to set up the machine to match that. So set that up with a direct rotary axis value. But in this case, we're doing everything around coordinate rotations. So you come in, I now probe 2 points, so I can cycle start, machine comes over, feeds, touches. Now, in this case, I'm going to follow my picture. So I'm going to move over. Maybe I know it moves up just a little bit. I cycle start. All right, I set my work coordinate. And that writes this value in. So if I go to the offset table, I now see there is a new value under the Z. So if I was to, see we're at 86.2, if I was to now instate this new offset, see originally we were at 80.775 and 24.5. So now I go back to swivel, I cycle start, and now we are 0 to this new location. And everything is set. So once we've gone in, we've rotated, we've oriented, everything's straight. Visually on the machine, the part looks straight. Now the final step in part setup would certainly be going to our measure workpiece, and then maybe even picking an edge kick, finding the center of a bore. My norm would be, finding the center of a block, right? Because typically I like to work this on a 5-axis, the center being 0, 0. But you'll just go through the steps you normally would in establishing the part 0 now at this point. Now from there, let's say I wanted to disable all of these offsets that are turned on, all this stuff. So what I can do is if I want to cancel this tool carrier, I want to shut it off, say, hey, don't compensate for this motion anymore. I can do that through the swivel cycle by strictly selecting 0 and hitting cycle start. Now, the numbers change, but the machine didn't actually move. That's just a compensation value based on the 0. I'm still not sitting at 0, 0, but now everything's off. So in this case, if I was to position to 0, 0, rapid, if you look at your machine, everything is square, right? It's at the original 0, 0. However, you do still have offsets in play. So you see how this have this little rotational symbol here? There still are values that are coming in and affecting us here because it doesn't delete these values. When I position based on my coordinate system, but I set it up based on these rotations, these will start to come into play with the tool carrier when I'm using swivel cycle, but not necessarily when I'm just positioning axes. That's why I was saying earlier, depending on how you program it, it's important to know that when I'm going to set it up. So if I was just strictly positioning the zeros and not using the swivel cycle, then I'm not going to get those offsets into play. It's not going to compensate properly. So if I want to clear everything out, certainly the final stage I would do, I'm just going to manually zero out all these calculated values. Now we come back and bump. Why do I still have a rotation? Bear with me one sec. Did I miss one? Nope. Let's just do, a lot of times I will zero everything out with the swivel cycle and then shut it off again. And that's the final. So now I have no symbols. Everything's back to the normal machine 0. If I jump back, I see I'm still sitting at the same point I was just at. Now, another simple way to cancel carriers as they're enabled and as things are starting to compensate is in the MDI mode. So I did mention that earlier, so we'll show you really quickly. Go to MDI. I can type a Cycle800, oops, typo, open close parentheses, end of program. This statement will also cancel whatever tool carrier is loaded. So you see my TC1 goes away there. That's very common. You see that type of syntax come out of a lot of KK packages for shutting off tool carriers, and that's okay as well. The one thing this won't do, and this is won't retract the head or anything, just cancel. So if the head was in some other location, I would have to manually start to move things out. Okay, so that's an overview of jogs. Certainly it gets a lot deeper than that, but those are some of the key features you'll start to use, especially when doing shop floor programming, because we're going to program specifically based on tool motion. So if we jump back to our PowerPoint, I want to start to get into the main context of programming. And we're going to start to look at Cycle800 in some detail here, because there's a lot going on. So there's two ways for Cycle800 to be utilized. It can be utilized for moving around the orientation of the machine plane. That's our unit coordinate system, or work coordinate system, WCS is usually referred to. Or you can use it to actually control the orientation of the tool relative to the workpiece. I would say your most common, and the example we're going to follow today, would be the orientation of the machine plane. So that's specifically what we're going to look at. So orientation of the machine plane, I see here that I'm on a normal G17 plane. So my tool is pointed straight down, and I'm looking right at the top of my part. Once the swivel cycle is instated, let me go back to that, it will come normal to this new surface. How do I start to swivel around? What am I using? Well, this is my interface screen. So similar to the screen you just saw in Jog, just with a lot more features and options. So you have a graphical input screen here. I can start to call up my records and start to define a bunch of different parameters as to how the result of where the rotors are going to go and where I'm physically moving it. So this would be a very typical screen that we're going to use, whether we're in shop mill or G-code. It looks almost identical, and you'll see it in both areas. So what does it look like when swiveling occurs? So on a table machine, you'll see that the physical table will be tipping over, and now the tool will come down and be normal to that new surface. So you see how my Z is now pointing at a new location. It didn't follow, the Z didn't follow the rotary because the system automatically compensated for that. In a head scenario, the table certainly would stay fixed because it doesn't move, but the end result becomes the same. The head now swings over, machine comes in. So the system itself can calculate for any number of different types of configurations of kinematics, whether it be your traditional swiveling table, like a trunnion table, or what we call a head-head kinematic. That's a rotary spindle. So what's happening here? So we got a couple things. We can stage our part 0, that you see with the red. We can apply a rotation that you see in the orange. And then we can do a final stage of the part 0 once we're in a new rotated plane. From there, we activate the command and it sets the tool normal to this surface. Just to show you what a few kinematic sets look like, we have nutated. We have our table Cartesian, We have a mixed kinematic, and we have a traditional head-head kinematic. So this gives you an idea of kind of what the motion would look like. So again, just so you can see, I believe I'm having a problem with our feed, so I don't think you guys are going to see the mutated table. Unfortunately, it seems like a little bit of a bug with this presentation software. It looks good on my end. But anyway, so what you have is head-head kinematic, as you just saw. There's two rotaries built up into the head of the machine. Whenever we refer to a mixed kinematic, that's going to be you have one rotary up by the spindle, up in the head, one rotary down on the table. You have what we call a table Cartesian system or kinematic, and that would be two rotaries down physically on the table. And then a table nutated, you can't see it here in the graphic, I don't believe, but it just means that the rotary axis isn't actually perpendicular to the linear. It's at some weird angle. So it's quite common at times, especially on some of your more advanced machines. Now, when we're performing swivels, there is this last field we touched about briefly earlier for our direction. So here you can see, based on the same values, there potentially will be, or there always will be, two different results. And we can control which the desired result is, in this case, which way it's tipping the A, based on that plus or minus direction. So as you start to methodize parts, you're probably not going to know which one you want until you start to run it. And then you're going to say, oh, gee, I noticed that the platter's swinging up towards me. It's okay, but now I can't see where the part is. So maybe I want to use the other direction. And that's where this kind of comes into play. So the kinds of swiveling, you do have the axis by axis that we're going to talk about in great detail because that's how we're going to use in our example. And then once you define it, rotation around the linear axis, then the rotaries move. You have what we call projected angles, so that would be a normal vector, and then you're defining angles based on that vector for them to rotate, probably the least common you'll find in the industry. And then we have direct axis, and that would be where I'm physically calling out the A or the C in the part program. And that can be done even with Cycle800 if you would prefer. You'll probably find a lot of CAD/CAM packages have a tendency to want to methodize that way because they kind of are used to that historically. Again, where it becomes a hindrance is when you're programming and you have compound rotations. It can be a little daunting to figure out which rotaries you have to move and when. But more importantly, what we're talking about now, specifically between axis by axis and direct, is the difference between what we call kinematic dependent programming or kinematic independent. So what that means is, do I want my program to only be able to run on this type of machine with these physical rotaries, an A and a C in this configuration? That would be what we call kinematic dependent programming. It's dependent on the machine tool. Or do I want my program to potentially run on any 5-axis machine? And that's called kinematic independent. And that right there is the beauty of axis by axis. So here, I can physically give it any configuration I want, and the system will automatically compensate for that. So my part programs can now be moved from machine to machine. That is really a game changer in the industry. Historically, a part program would be programmed, posted, and tethered to that specific machine tool. But between the ability of managing where the rotaries are in space through functions like our tool carrier and Cycle800, and then the ability of positioning values that aren't dependent to a machine tool, this axis by axis, this kinematic independent positioning, we now can have programs, a single program will run on any machine type. Head, table, mix, nutated, doesn't matter. So we're going to go in, we're going to create a part program, and we're going to use, in this case, shop mill first, and then we'll look at G-code after fact to physically part program a job. We're going to use the standard part programming interface. So if you've attended or done any shop floor programming on our machine, you're going to see a lot of functions that you already know and use. But we're now going to use the swivel cycle to start to move around our part 0. So it's important to kind of visualize where the 0 is initially staged right now. So in this case, this part will have been set up with the 0 at the lower left-hand corner. And my unit coordinate system, shown to you by this little axis cube that you see sitting on top of the part, this is what we call a coordinate cube or an axis cube, will be sitting parallel to the machine's platter, or the bottom of the stock. So if I was to send this to 0, 0, 0 on our swivel cycle, like we've already been looking at, or in this case, I cancel all and just do a basic retract, my plane, my tool plane, should be perpendicular to the bottom of the part, not this 9-degree slope. From there, we're going to start to use the swivel cycle, talk about all the key inputs that you're going to plug in, and we're going to start to potentially shift our 0, rotate our axes. So here you see I have a negative 9-degree rotation about the X. So that actually on the physical machine created a 9-degree rotation in the A axis, and it tipped it down. So I see here, this is the result of where my unit coordinate system will move to. From there, we're going to start to place the unit coordinate system and make my tool normal to these different 45-degree planes, and we'll do that through our different screen inputs. We'll proof out in stages as we start to add different features in our standard simulation. And then from there, we'll get an opportunity to look at the machine space model and show you what's really happening in real world, so you can start to conceptualize. And this is all based on conversational programming. That would be in an auto mode. So we're going to do this with a live demonstration, again, through CineTrain. So what I do want to do is I want to bring up the part print, so you have it here in front of you. So now you can kind of keep an eye as we're inputting data as to kind of where I'm pulling this data from. So let me just move this over just a little bit. All right. Good. So we're going to go to Program Manager. We're going to start writing a program. And this is going to be the same method that we've always done in the past. So if you need a little more detail on the basics of Program Manager and creating part programs, specifically with Shop Mill, I would strongly suggest taking a look at my webinar page on our CNC for You website and looking at some of the previously held seminars. The website, in case you don't know it, is www.usa.siemens.com/CNC, like computer numerical control, so CNC, the number 4, and the word YOU. So you go to that website, usa.siemens.com/CNC4U, and you can access any of my previously held webinars as well as this one. Okay, so we're going to write a new program. We're going to create a shop mill program, and I'm just going to call this example. Oh, let's put my caps on. Not that it matters. Example 1. So any name I want, say OK. Launches me into the standard header that I'm used to. So I'm using work coordinate number 1. That's fine. Doing a basic block. Set up some 0 points for my simulation. So in this case, lower left-hand corner 0, 0. I'm going to set my values to absolute. And we're going to say we got overall width is 100 millimeters by 100 millimeters. I don't have any positive stock because we're going to machine a 9-degree plane, so I'm not too worried about it. My thickness is off my print, 65 millimeters, so I want my top of my part to be 0 in this case. So I'm going to say that my stock exists in the negative direction. Your base tool plane and swivel is always going to stay G17 because I'm going to actually move the unit coordinate system, so the tool is always normal to Z. Sitting, parallel to Z, I'm moving Z around and making the tool go normal to that. So you're just going to stay in G17, like you always have. Retract, where do I want to go when I'm done? How close do I get? This is all our typical functions, down cut, up cut, climb mill, conventional mill. And how do I want to drill? Do I want to optimize? So you fill out the page, just like you already know, hit accept, and now we come in. So probably one of the first things I'm going to want to do, I don't necessarily know where the rotaries are staged. Maybe the table was left at some position, maybe somebody jogged it around. So probably the most common thing to first do when starting a swivel cycle program is go to Various, go to our swivel plane. This is where you can find the swivel cycle, and do an initial settings calling up my carrier and retracting my Z all the way to the top, just like I've been doing in the jog screen, and saving it. So this will force the system to shoot back up, zero it out. Now, if I'm on a machine and I'm using it as a standard 3-axis machine, and I don't even care about the rotary motion because nothing's going to move, my next scenario would basically be shut it off. So I can cancel all the tool carrier. It's disabled now. It's completely shut off. And then I could just progress with using this machine as a traditional 3-axis machine. If I'm on a 5-axis and I don't want to use it as a 5-axis, I would still get used to doing this example right here. Make sure everything's square and straight. Shut off my tool carrier. Now, in this case, I don't necessarily need to shut off the tool carrier because I'm going to be using it the whole time. But the first thing I need to do, once I know everything's clear and it's happy and it's a safe spot, is I need to machine, to look at your print, right there in this middle view, this first projected view, I need to machine a 9-degree plane. I got to machine off this face 9 degrees. So I'm going to do that with the facing cycle, but I'm first going to get my tool in orientation using the swivel cycle. So go to swivel, turn it on. Now, a couple extra features you do get in conversational over the G-code side or over what you saw in jog. And one of the first things would be, actually probably this is about the only thing you're gonna get, is the ability of doing tool changes. So if I wanted to handle the tool change right now, I could. If I want to handle the tool change later down the road in the cycle level, I could do that too. I think where I would be more concerned is if I was on a machine where the rotation could affect the tool change, like a head-head machine, where if it's rotated and I tell it to do a tool change, I'm now relying on the machine builder to make sure they bring that head back before they allow it to tool change. So in a case like that, I may load the tool and then instate my rotation. So there might be a couple extra steps involved, or do it from this screen. In this case, since it's a trunnion and she's going straight up to do tool changes, this wouldn't hurt me, so I'm just going to leave it alone. I do always want to, even though I know it's already there, make sure she's retracted. It's a good habit to always get into. Now, new or additive. I talked about them briefly before. We'll use it a little bit later, but think of this as the difference between absolute and incremental positioning. So we want an absolute position. Do I want to stage my part 0? So that's very handy when I start doing part programming, especially on the machine, because based on the dimensional data, when I do my rotation, I don't want my work coordinate system to be left somewhere in space, because I might not know from that point where my part planes or my features dimensionally are. So you'll find you move it around. On this first one, I'm going to leave it right here in the lower left corner, all right? And now I want to tell it how to rotate. So I can do my kinematic independent, my axis by axis rotation, or rotations around a linear axis, or I can do my direct axis. In this case, to make it kinematic independent, so I can run this on any machine, I'm going to do axis by axis. Now, you do have the ability of picking the order of operations, and this is very important if you're doing multiple rotations, because it's going to do it as a sequence of events. So it's going to physically apply the rotation about X first, then Y, then Z, or any order of them. If you're only rotating one axis, which we are, really doesn't matter. If you want to get in the habit of always telling it the axis you're rotating as the first, that's okay too. So here we're going to do a 9-degree, and it's a -9. How do I know that? The best thing you can do when you're getting into programming in 5-axis is get yourself a coordinate cube. The coordinate cube looks like that little image I was showing you, but it's a physical cube you can have in your hand, and you can tip it around in space and start to see the direction that you would need to go to get the tool normal to that angle. So I happen to have one in my hand, and I know that's a -9 degrees. I'm not moving Y or Z, and I'm not doing any final staging of my part 0 once I'm rotated. We'll do that later. And we're going to default it to a negative because I don't know if I want a different direction. So I hit accept, system tips down. Now I'm going to go in, and we're going to give it some cutter path. So I'm going to use a simple facing cycle. I'm going to go grab a tool. I'm going to use my 20 mil cutter, give it some speeds and feeds. I'm not worried. We're not going to really machine this. We're going to rough it out. And now I'm giving it the values based on my coordinate system dimensions. So remember, my 0 is still in the back left corner, so that's okay. But potentially I have some plus stock because although I tipped down on this corner right here and my part was flat, when I get to the far end, I got a bunch of material here. And I don't know how much material I have there. So you're going to you could either calculate what the height of that triangle would be, and that would be the height of the material on that side, or you can just leave yourself some material like I'm going to do, and then take a look at simulations and see if it's realistic or not. Then from there, you define the overall, just like you would in a normal facing cycle, so 100 mil. Now, my Y isn't really 100, because 100 would have been relative to the top. But I'm coming down this plane, so I see that the overall dimension of that is 101.1. I could tell this 102 just to make sure I clean everything up. My absolute end position was going to be a 0. My step over is going to be 65% of my cutter, let's say. And my depth per cut, we'll do like 5 mil and no material for a finished cut. Okay, now, very common practice. If I wanted to check this right now, usually whenever I turn on a swivel cycle, I like to shut it off. So a lot of times I will add that to my part program as I go in stages. So just the initial. All right, make sure my head's retracted. That's going to set everything back. And then I can do my final shut off. I don't need to retract here because I'm already retracted. So that I'm just going to let move down in my part program as I go. That's a very typical shut off type of scenario I would see. So if we go to simulate it, we should start to see what it's going to look like to work in 5-axis orientation. So if I look at 3D, I see I'm now machining on a 90-degree plane. So that was that 102 mil or that 101.1 because I'm down that slope. And that is my first cut. So I look good so far. So we're now going to do really a lot of the same thing. I'm going to go back. I want my highlight to be on my face mill because I'm going to continue on. And now I'm going to machine these 245s. So I'm going to go back to various, go back to swivel plane. Turn her on, make sure I'm retracted. Now I don't want to move my X and Y 0. I'm going to work on this lower left-hand 45 right here, as you see on my cursor running around it. But what I do want is I don't want to do the rotation where the 0 is right now, because remember the 0 is up here on the top of plane of the part. Well, that once I rotate, that's now going to be in space. And I don't know the distance from where these two straight lines would intersect down to where this plane is. But what I do know is I know if I drop my Z 30 mil and then rotate, I'll be right on the surface plane. And then I'm just guessing on how much material I'm leaving in the plus, which is a better guess. So I just want to move my Z down minus 30 mil. Now, I said earlier, if you want to get in the habit of changing it so the axis you're rotating is going to be the first axis, that's okay. We're rotating a Y of negative 45 degrees. I don't want to do anything else. So now, right now, once I'm done, my unit coordinate system is going to be sitting here right at this corner. Z is going to be straight up, perpendicular to that face, and X is coming up this plane. So all the stock exists in an X positive and on a Y positive moving down that surface. So I've orientated it. We go back to our face mill cycle. We're using the same tool. I don't have to keep calling that up. 0, 0, top, we'll just guess at 10. Now, I don't want to leave 100 because I know that this surface is only 42.4, so I'll say 43 mil in the plus. And I know this is truly 100 now because I'm now parallel to the Y. And I'm going to end at 0, that's great. And the rest of the stuff I can leave alone. It should be okay. So we just knock off 145. Now we jump back to swivel cycle. Now, you can either go back or you can certainly cut, copy, paste like we do in any other program. So I could paste this down. So in this case, I want to shoot my 0 over to the far corner. So I'm going to move my 0 over 100 mil. And then I want to drop down to this lower corner. If I knew where this position was, which I don't, but if I did, if I had that dimension, I could have moved to that point and then did a rotation. And then all my stock would have been in the plus direction. In this case, I'm going to be rotating right from that point, that negative 30, and I'm going to be doing the opposite, so a positive 45. So now all of my stock exists in a negative in X. So if I grab the swivel cycle, or shall I say the face cycle, paste it, and just merely change my direction to negative 43, we now start to see machine to 45, machine to next. I'm going to get rid of my path. You will start to see a lot of these circles representing the rotary motion. That's normal. We just want to show you the end result here. Okay, so everything looks good. Now, certainly, if I mess something up, now would be the time I would see it. You know, like let's say, for argument's sake, just to show you real quick, I forgot my plus or minus. Oops, that's a lot of big of a mistake. 45. So this is where it's great and so important to have the capability of having some 5-axis simulation capabilities right on the control. Because if not, you're really flying blind. So that's one of the things that by us adding, and that was new to Operate, this 5-axis simulation capability, it really makes shop floor programming feasible. So here I can see, yeah, that's the problem. I totally botched that up. So I can say, oh, well, where did I do last? Oh, yeah, I did this swivel. Oops, went the wrong direction. Okay. So now I want to come in and I want to put this pocket on the part. So I'm going to be back here after face melt. We're going to, in fact, I want to go back to my first 9 degree. So I'm going to copy that. And this is going to place me, let me paste that down here. This is going to place me at this 0. Now, instead, though, dimensionally, I know the center of this pocket, right, down here. So maybe I don't want to work from 0, 0 being the center of the pocket. This is where a case where I would stage my 0 over, apply a rotation, and then stage my 0 down, because I know relative to the surface, the center of that pocket's 50 mil down this plane. It's down there. So I couldn't do the 50 mil up top because that would have been in space and then rotated, and then my 0 location would have been off. So again, all this stuff depends on how it's dimensioned. So now we can do a pocket mill, circular pocket, same tool, feeds and speeds. I got to check my other feeds and speeds. I think I left them a little low. And we'll do helical, we'll do a single pocket, 0, 0, 0, right, because I'm on that plane. Diameter is 30 mil. Depth is going to be, I'll do an absolute, minus 10 mil. Step over is going to be 50%. Pitch, that's fine. No finished material. Okay. And I just wanted to double check as we go through. What do I got? 500. Yeah, my feed and speeds look fine. Good. So that will place that pocket in. Now, once I machine the pocket, I do want to come down here on this corner, rotate, and machine that 45. So this would be a case where I'd want to use the additive function because I have a 0 staged. I know this edge, right? So I can get to that corner. I can do an additional 45 degree of rotation relative to this 9 degree because I see my angle is based on this plane, not the top of my part. And then I even know how far I need to shift my 0 in here to get on that surface or leave it in space and just position it down. So this would be a perfect case for doing an additive as opposed to a new. So I'm saying wherever my 0 is, I'm going to move it again an additional 101.119. Oh, no, sorry, 50.1, 51.119. I'm moving an additional, so I'm saying, hey, you were 0 here. I know that's 50 mil, and I know the total is 101, so the difference, I'm going to move it down that plane in the Y. X doesn't change because X was dead center of my block here. Once I get there, I'm doing a rotation. So now, what am I rotating about? I'm rotating about my X, right? And I'm rotating about my X, an additional negative 45. So that will get me to that orientation plane. If for some reason I didn't want to position this in X along that, maybe I wanted it in Y, you could certainly do like a negative 90-degree rotation that spins the whole work coordinate system. So now I'll be positioning in a Y, even though you would think that it would be X motion. But what I need to do here, if I want to handle it at this point, I can also shift my 0 down based on my print 2.83, a negative 2.83. Now I have a 0 set right on this surface, right in the middle of the part, and I'm ready to chamfer. So how do I handle the chamfer? Certainly a simple way is to just give it some line moves or position moves. So I'm going to expand over, go to straight circle, pick a straight move. I'm going to rapid to X of 0, Y of, let's say, negative 50 mil, Z of 0. All right, so I'm rapiding right over here, right in this corner, where I know there's no material because it's already been chamfered off. Okay. I'm now going to do a straight move in Y to positive 50 mil. And we'll say 500 is fine. Once I get there, maybe I'm going to do a straight move off. Let's say 10 mil in a rapid. All right, we just cleared that chamfer. Okay, so if I start to simulate again, we should have a pretty complete part minus the drilled holes. So let's take a quick look before we get too far ahead of ourselves. So this is what we've known and we've seen already. This looks great. There's our 2 cuts. There's our 45. And I probably would obviously take a couple extra cuts if I was going to really machine this in real world. So there's our corrected 45 on the other side. There's my pocket. And there's my little chamfer. All right, so we're looking pretty good. Now I just want to go in and put a bolt hole pattern. So edit it. Once I'm here, I'm going to go. Now I do want to reinstate my previous swivel, right, because I don't want to keep my 0 where it is. So I'm actually going to use this one, and we'll bring it right down there. So that is putting my 0 back to the center of my pocket feature, and I'm sitting at a 9-degree rotation. We're going to go drill some holes, do some basic drilling. We'll use the 8mm tool. I think I have an 8.5. That's fine. All right, so we're going to drill a couple holes. Not worried about my speeds and feeds. I'm going to position based on my tip. Let's say this is an absolute, and I think it was 10 mil. Yeah, 10 mil down, no dwell. And I do just like I normally drill. I'm going to link it to a bolt hole pattern. Top 0, 0, 0 center. All right. So I know my included angle on this. I got 120 degrees. The radius I happen to know is, well, I know the diameter, so I'll calculate it. I have 3 holes, and actually no, I want to start at 270. Sorry, I'll start at 270. Okay. So we come down. It does its thing. My shutdown from earlier is still there. So when I'm done, I'm going to retract, square up the table, and shut everything back off. So if I do a final simulation, I should have a complete part. So we come down. We do have an option if you do Control-M. It's a cute little trick. It's going to jump your simulation right up to its max. So shoots it up. There we see we got some drilled holes. Okay. So I simulated the part. I'm pretty confident. I'm ready to run my part program. So just like I would in any program, stage your highlight at the top of the part program. We're just going to try to start from there. That's one of the ways we can do a mid-program start. Jump over to execute. I'm going to minimize our print here. We don't need that now. And now it would run like I would normally run. So cycle start, it's going to look like I would traditionally run any part program. I can bring up basic blocks if I want to see the G-code commands. If you look at your G-code functions, you can start to see some of the commands stated here. all G-code functions start to show you rotations, different compensations. She's jumping around, doing her thing. So RAM machine the part. Now, the one thing I do want to show you here, and we can play around with our simultaneous record, and we can go into our machine space model, is what the motion of the machine would actually look like. So if I zoom in a little bit, so this is going to show me, as I run it, keep my feet right down a little bit, what the actual motion. So there's your 9 degrees, right? There we're machine up the plane. So it just tipped the table just a little bit, just enough. There it spun around. So now the Y is pointed that direction. Oh, and there I get to see she flipped to a weird location. So that was that plus or minus. So if I rotate this down, we see the part. So the part is sitting, staged in the machine. All right. So now what we're going to do is we're going to jump back to the PowerPoint. Now that you're starting to see the base motion, we're going to take a look at G-code, and then we're going to get to play with this machine space simulator a little bit more, because we're going to manipulate things around and show you how we can change some results. Okay. So example 2, which is pre-created, so we'll just copy it in and take a look at it. Starts to show you the exact same part methodized with G-code. So what we'll do is we'll open up, we'll show you the data mask for the Swivel Cycle. If you've attended any of my G-code webinars in the past, you'll start to know data mask and what that's all about. And then from there, we'll start to use the simulation tool to start to look at it. So you'll notice it simulates, the tools are identical between the two. But now we can start to play around with the machine space mode and maybe change the plus or minuses to change results, start to manipulate the system around. There are some key features, whether you're G-code or shop mill, it really doesn't matter, that will help you when you're starting to work with, especially with 5-axis type programs. Overstore is very handy. We'll explore that here in a sec. That's kind of like having a little MDI built-in auto. Block search mode with our scanned calculations is incredibly important once you get to 5-axis if I want to do any type of mid-program restart. And then the other ones that I use quite a bit are the PRT and dry run mode, and also the rapid reduced travel mode. All three of those are very handy, especially in some of these 5-axis machines, because they go at very high rates of speed, especially these rotaries. And a lot of times I don't want to run anything if there's potentially an over-travel issue. So we'll explain that more in a second here. And then we're going to go, and we're also going to talk about the beauty of how this is completely now independent to wherever I stage my part. So we'll move some zeros around, and you'll see that the program will dynamically adjust for it, and it's going to handle it however it needs to handle it without me having to change the part program at all. Okay. So let's jump back to CineTrain. So now, from a programming standpoint, if you look down here in my examples, I have a G-code version created. So this is the way it's going to look like in G-code. Certainly, I'd have to do my normal safe start header type of thing. I'd have my blank, just like I've done in the past, so just like you saw where we were. And now I'm going to go to various, go to Swivel, just like you saw over in Shop Mill, but now you're going to see this is the data mask here for Swivel Cycle. So I'm putting everything to a normal location, zeroing it out, right? I didn't bother canceling in this case because I knew I was going to go right into Swivels later. Tool changes, spindle commands, this is all your traditional G-code. And then from here, you're just going to use the same data mask. So it works the exact same way you just saw. Staging to 0. Really, the only difference between the two fields is you don't have the ability of tool changing here in G-code. Just like in a standard CAN cycle, you wouldn't have the ability of tool changing at the CAN cycle level either in G-code. The same rules apply. So basically, once you know how to use any of our cycles, all the contour mill, all the irregular pockets, and all this stuff, you can apply them at any orientation, and that's the beauty of Cycle800. So everything that you now know as a capable 3-axis programmer and machinist can be applied in a 5-axis orientation with Swivel Cycle. So this is the basic mechanism like we would see, just In this case, cutter path, I'm using a facing cycle, orientate, cutter path, orientate, cutter path, orientate, pocket, cutter path, orientate. Here I just did some simple rapid moves to handle my chamfer, right? I sent everything, I repositioned my orientation to my 9 degrees, loaded my drill, and then drilled some holes. At the end, brought the head up, brought all the rotaries back to space, canceled my carrier, just like you saw earlier. So the mechanism's identical. It's just really the nuances between G-code and conversational is really the difference here. So we come in, we start to look at it, start to see our motion. So you'll notice, ironically enough, it's going to look very similar. It's going to look the same. So we see a chamfering our 45s. So whether you're posting from CAM, which is going to be very common in this type of technology, or writing on the machine, you'll be able to simulate the same way, either scenario, no matter really how they're part programming, but preferably if they're part programming using Cycle800 functionality. Okay. Certainly from there, we can jump over to execute when it's time to run. You do have the machine space model. Now, this machine space model, this isn't going to be on very many machines. I wanted to use this so you guys can conceptualize what the motion looks like. But this is an advanced feature called collision avoidance that we sell. But it is a very expensive mode, and it's really new to the system. So you'll probably start to see it coming out more and more in the near future. Don't expect your machine to have it or go looking for it. It won't be there. Traditionally, like I said, only those very, very expensive, very advanced machines may have it. But you will probably see it more popular in the future. I like to show it here because we don't have a machine in front of us. So this is the next best thing to having a machine in front of us. Now you see this case, the rotary didn't swing out. So that was a case, if we jump back into that rotation, that the plus or minus would have been changed. And I pocket it out, chamfer, bolt hole pattern, set it back. Everything's back at 0, 0. If we zoom out a little bit, you'll see it's all squared back up. And that plus or minus, that can be a neat way to stage things. If I wanted to maybe present the part at the very bottom. When I'm done, I could have said, hey, rotate the other way when I ended it. And now, I'll crank up my speed a little bit. Now you see what it's doing. She starts coming around. Oops, rotate. Chamfer in. Bolt hole pattern, and see how it spun the part around? It's now faced it to me. So that's just the difference of results. So as I start to use the machine, we were talking about kinematic independent. I want to give you an example of that. So let's say, for argument's sake, in this case, I have my block, my stock sitting dead center in my part. So if I was to look at my offsets, this machine's commissioned with the machine 0, center of the platter. So if I come out, look at my offsets, I shifted everything -50, -50, half the width, half the depth, in a negative direction to stage the block 0, 0. If I had left these at true 0, and I went back and ran it, now you see the part shifted over. But I haven't edited the program. The system's automatically compensating for wherever the part is in space automatically for me. Same thing in the Z-plane. So right now, if I look at it straight ahead, I notice there's no gap. Part's sitting right on the block, but potentially there's a vise or something here, right? So if I had shifted things up, 100 mil, and ran it, now you see it's up in space. Tipping, doing its thing. So everything's still good. But what happens if I had positioned her when I threw my vise down and whatever fixturing or whatnot at a position, and let's say I did, I don't know, let's do 100 here. 100. All right, some crazy location. Oh, I immediately see I got an over travel software limit switch. Now, this is a problem. This is certainly a simple scenario, but I might have been down in a pocket. I might have been in this weird location when this over travel occurred. See, just because I use simulation, back here over here, it's regular simulation, the system's not going to evaluate the travels of the machine at this point. So it's going to come in and it's going to look like proper part. In this case, it's showing me in a weird location because a rotation was left active from the previous. So I'm going to let this actually shut itself off. So let me run that again. You'll see. So it's happy, it's doing its thing. So right now, I have no idea running this thing that I'm potentially going to, that was a little funny. I'm potentially going to have a scenario where I'm going to have an over travel alarm. So when looking back here, and I'm about to run something, one of the first things I like to do in the 5-axis world, because the worst thing I want to do is have stage something, go to run it, I'm in the middle of machining, then I get an over travel, is use under program control my PRT, program test mode, no axis motion. So what this means is as I start to run the system, she's running, she would have gone as far as it could have gone. Maybe I had a case where probably if I drop this a little bit, it may get a little further in the program. Let's see. She's running. See if we can get it to over travel a little bit further down, depending on how close where the rotation is when it. Yeah, there you go. So I was already 3 or 4 operations in when she tripped out. Well, what's happening right now, since program test mode is on, if you look at your machine, no axes are moving. So it's just running virtually. Now, it's running real time, but the beauty is I'm not now stuck in some position that I have to try to correct or get out of. I could, I now have the ability of saying, oops, why do I have an over travel there? Backtrack it. Maybe I need to move the part position somewhere else. Now, the other thing I don't certainly like to do is waste a lot of time. And if it's a long cycle time, I don't want to run this real time. So then I'll leverage the dry run mode with the PRT test mode. Cycle start, it's going to run at a much higher rate of speed. Over travel, I now can start to go in, maybe adjust where she is in space. Maybe I was able to drop the Z a little bit from a fixturing standpoint, whatever. And now I can see still have a little bit of a problem. So maybe I would have needed to move the location of my fixturing a little bit, and then keep on rerunning the test until we can get all the way through the scenario. And let's go here. But again, I'm doing this, and she's now fully evaluating the work coordinates, 0 locations where everything is in space. So you're going to start to use this quite a bit. Now, another thing that's very popular on these high-performance machines is rapid reduce travel. So when RG0 is turned on, you'll get an RG0 field. The system, if I span my horizontal keys and go to settings, the system will now reduce the rapid travel to whatever value I have here. So now it's going to cut all my rapids at 50%. So now as you run the machine, really run the machine, and running it real time, the rapids are going to be cut 50%. So that's going to give you a lot more reaction time. These rotaries, all these rotaries move really quickly, especially when the tool is close. So that's very, very handy mode in the 5-axis world. Now, the other one that's very handy is our overstore function. So what overstore does is, let's say I'm in the middle of running, I forgot a coolant or forgot this, forgot that. I can cycle stop, I can go to overstore, and I can now start executing. Delete blocks, goes from my MDI. I can start executing different commands. So turn my coolant on, cycle start. Coolant fires up. Or maybe I'm rotated at some orientation plane and I say, let's come back. So we're in, we're running, I cycle stop. Maybe I need to retract. I can come over here and I can say, hey, do a G0, typo, sorry guys, and Z, I don't know, I want to go 50 mil above, cycle start. She moved up to 50 mil, see right here. So I can stage it, I can get in, I can shut my spindle off, I can check some things, but when I come back out of Overstore, she'll do, and I'll slow it down here. So she'll do a reposition and then continue cutting where I was at. So it gets really handy, especially in 5-axis, a head machine, let's say, or a mixed like lathe technology where I see you have some bars shoved in some side bore. I can do pullouts, and it's relative to all the offsets that are currently active or running. Okay. So from there, I believe that's all the content that we wanted to get through today. Certainly there was a lot of content here that we talked about. So we're just going to jump back to our PowerPoint. At this point, we're going to open up the floor for questions. I know we're running long, so I'm going to stop the recording. Certainly stay for any questions if you guys have any. But thanks again for joining me. I really appreciate it. Hope you found this interesting. So give me 1 second. I'll be right back.